Okay, before I start, I have one announcement, which is shown here. It'll be in the notes. So NSM Student Leadership is hosting a research night. It's still a ways away, April 20th, so about 3 weeks, Wednesday night. It'll be in this room at 5:30. And the idea is to introduce you to research opportunities in NSM, learn how to find one, meet some specific professors who are doing research and interested in having undergraduates do research with them. So whatever your major is, I encourage you to strongly consider doing undergraduate research. I think it's a great way to learn about your field, and I think it's a lot more fun than sitting in class and learning things that were already established hundreds of years ago. And in research, you really get to be at the forefront of new knowledge and generating new insights, which is always, I think, a very fascinating thing to do. So please come to that if you're interested. I'll be there, which I don't know if that's an enticement or a deterrent, but nonetheless, you'll see me if you come to this. And then the other thing it says here, which I think is kind of hilarious, is they suggest to bring a resume. That's not a bad suggestion. But then they also say, please dress in business casual, which is kind of funny to me because the number of professors who would care about what attire you're wearing or something like this is pretty much zero. But nonetheless, if you want to follow their instructions, then come in business casual, but that part probably doesn't matter so much. Okay, so that's coming up, and if you look at the completed notes in Blackboard, that flyer will be there so you can take a look at that in more detail. All right, and then the other announcement that I have is, with exam due in the books for just about everybody, so if you want to come talk about the results for that, or you want to see what your standing is in the class, we're past the halfway point now. We're close to the drop deadline, so this is kind of an important part of the semester to figure out where you are. So I'll have office hours today after class, and I should be there until 2:30. So if you want to come anytime during that time, I should be around. And then also tomorrow, officially, it's going to be 2 to 3 p.m. But if you need to come if you want to see me at a different time than that, let me know. I have a little bit of flexibility tomorrow. Yeah.
For the NSM research night, do you know if there's going to be research opportunities for colleges outside of NSM, sciences or something like that?
As far as I know, that event is just going to be NSM professors. So if you're outside of NSM, you can still do research in an NSM department if it's interesting to you. Some professors are particular about what majors their research students are, some are not. And then there is an Office of Undergraduate Research on campus that would have information about all of the opportunities around UH. So if you want to contact them or visit them, that's also a good way to learn about those types of opportunities in other colleges. Anything else? All right, so with that, we'll get started. Again, we're going to continue with Chapter 7. So this week's homework assignment covers most of Chapter 7, and this is the topic we're going to cover now is the last thing. And actually, we covered this several weeks ago. You probably don't remember at this point, because I barely do, but the book rearranged itself this year in the new edition of the book. This is my first time teaching out of it, so I mistakenly covered it at the wrong time. So we're going to cover it again here at the appropriate time, and this is another method for finding delta E or delta H for a reaction. I'll say that this can be, again, we use those two terms almost interchangeably, and at this point it'll be more common to see it as delta H. So last time we learned a way to calculate delta H, which is pretty straightforward. It requires you to know the formation enthalpies, the delta H of formation for all of the reactants and products, and then you just take products minus reactants to get delta H for the reaction. This is another way to do it, which we learned about this again back in Chapter 3 when we were introducing bond energy, although these actual types of problems don't really come into play until this chapter. And this is where we're going to be using individual bond energies in reactants and products. Now, on some level, it's not as convenient as delta H of formation because it requires you to tabulate more numbers, because you're going to have a number for each individual bond in the reactant and product, not just one number for the whole reactant or one number for the whole product. And you have to include elements like N2, O2, and things like that, where the two atoms are bonded together. Those still have a bond energy associated with them. The convenience of this approach is that the delta H of formation is not known for every substance in the world, but bond energies for pretty much any combination of two atoms are known, and so we can use this again in situations where those formation enthalpies are not known to us. So here's sort of the strategy we're going to take. Again, we covered this before, but let's review it today. So first we're going to assume that we're going to break all of the bonds in the reactants. Remember that when we do a chemical reaction, we're rearranging bonds. We're taking atoms that are bonded together on the reactant side, and then making new bonds on the product side to make new substances. And so the way we approach this is we're going to estimate delta H is first we're going to break all the bonds on the reactant side. And remember that this requires us to put energy into the system because those bonds are holding together two nuclei via attractive forces. If we want to break them, we have to put energy in. So that step's going to be a positive delta H, breaking all the bonds. In the reactants. And again, we have to do this for every single bond that is present on the reactant side. And again, that's the left side of the equation, so I don't need to mention that at this point. And then we're going to form all the new bonds in the product. So we are going to figure out how much energy is released when the new bonds form. So when two atoms come together and form a bond, energy is released. It's an exothermic process. And so a different quantity of energy will be released once those new product bonds form. Now, this is not actually how chemical reactions happen. When we do a chemical reaction, we don't typically have the reactants completely atomizing and then combining on the product side. That's not how it really works. But again, this is a thermodynamic type of approach where all we care about is the final and the initial state. So we just care about the bonds in the reactants and the bonds in the products. And the difference between those two will give us the enthalpy change for the reaction. So even though it's not the path that a real reaction would take, it is a valid way of calculating those enthalpy changes. So when we form the new bonds, a different quantity of energy is released, and again, that's going to be an exothermic process when we're forming bonds. And at least some of the bonds in the reactants and product side have to be different for there to be a net reaction. However many products there are. And so then that leads to an equation that's actually pretty similar to the one we gave you last time for delta H formation, but what you have to remember and not be confused by is that this time instead of products minus reactants, it's going to be reactants minus products. And that's just because bond energy and delta H of formation are defined differently. Delta H of formation is the energy associated with forming a compound. Bond energy is the energy of formation, the energy associated with breaking a compound apart. Since they're defined in different ways, the equation that comes out for estimating delta H for a reaction ends up being opposite. So when we're using bond energies, it's going to be reactants minus products. We're going to sum up all the bond energies on the reactant side, and then we're going to subtract all the bond energies on the product side. So we have to make sure that we keep those two methods straight. Formation enthalpies, products minus reactants. And for bond energies, it's going to be reactants minus products, where again, sigma means sum. It's the Greek letter that we mean sum, and then BE refers to individual bond energies. And just like last time, we have to make sure that the equation is balanced and that we appropriately count how many of each bond there is on the reactants and product side when we add them together and then subtract them. So when I introduced this a few weeks ago when I wasn't supposed to, we sort of said that it's more like accounting than chemistry, because all we're going to do is we're going to just tabulate a bunch of bond energies on one side of the arrow, tabulate the bond energies on the other side, and then subtract the two. So this is the example we worked through, so let's go through it again. So we have this reaction here. This is called formaldehyde. It's reacting with phosphine, which is a really nasty substance, to form this type of product here. So the phosphorus hydrogen is adding across the CO, and we're getting that as our overall chemical equation. Again, we're going to calculate delta E, or as it will be more commonly stated, delta H, for this following reaction. All right, and here we're not given delta H of formation values, we're given individual bond energies. So again, a bond energy is just the energy to break one bond between two atoms. It's not going to apply to an entire reactant or product in most cases. It's going to apply to just a single bond in that reactant or product. And we have to make sure we're using the correct bond order because, again, here we have C double bond O on the reactant side, we have C single bond O on the product side. Those have two different bond energies, so you have to make sure we're using the correct one. So it's important to know what bond order you have in your reactants and products as well. So all that stuff we kind of already have built up throughout this course, so now we're just going to use that insight to be able to calculate delta H in a slightly different way. So as I said, we're going to sum up reactants and products and then subtract the two. So let's do the reactant side first. So in this first reactant, we have two CH bonds, carbon, hydrogen, carbon, hydrogen. And so the energy for that is going to be 2 times the CH bond enthalpy, which is 413 kilojoules. So that's 826. We have a carbon-oxygen double bond in the reactant. And then we're going to have 745 for that. And then we would have pH 3 is going to have 3 phosphorus hydrogen bonds. It's going to be phosphorus with 3 hydrogens around it. So that's going to have 3 pH bonds. And the pH bond enthalpy is given here is 320. And that's going to be 960. So the sum on the reactant side, which is half of what we need to do, is just going to be those 3 numbers added together. And that's going to be 2,531 kilojoules. So that's reactants. Then we have to do the same thing on the product side. So on the product side, we just have one product, but it has a lot of different types of bonds in it. So it's still going to have 2 CH bonds, CH and CH. There's 2 CH bonds. So that number ends up being the same, 2 times 413 kilojoules for the CH bond enthalpy. And then this time, as we already mentioned, the carbon-oxygen bond is no longer a double bond, it's a single bond, so it's a C single bond O. So the appropriate enthalpy for that is going to be that number there, 358. And going through the rest of the product in any order, we have an OH bond. So OH is going to be that last number there, 467, one of those. And then we have carbon phosphorus and 2 phosphorus hydrogen bonds. So there's a lot of different bonds in this product, so we have to make sure we count all of them. So there's 1 carbon phosphorus bond, and that enthalpy is given as 264. And then we have 2 phosphorus hydrogen bonds, each at 320. So this time instead of 3, we have 2. And so that sum on the product side is 2555. And that's the sum on the reactant side up here. Didn't write it out, but that's the sum up there. So then we just have to subtract those 2 numbers. And again, it's going to be reactants minus products when we're doing bond energies. So the delta H then is going to be just bond energies on the reactants minus the bond energies on the product side. So the first number we got for the reactant side was 2,531 kilojoules. The second number we got for the product side was 2,555. And so we predict a relatively small but still negative enthalpy change of minus 24 kilojoules for that reaction. All right. So again, it's just a lot of accounting more or less, just to make sure you're counting all the bonds and adding up all the numbers correctly. One thing to be aware of that this problem didn't have was coefficients, but if we had a reaction where, let's say, one of the products or reactants was 2H2O, remember that each H2O has 2 OH bonds, and if there's 2 moles of that on the reactants or product side, that's a total of 4 OH bonds. So make sure you also account for coefficients when necessary. We didn't have to do that here. This is just a 1-to-1-to-1 reaction, but in some reactions you'll have coefficients as well, and so when you're counting the bonds, make sure you account for the coefficients as well, and not just the individual bonds in one molecule of that reactant or product. Okay, any questions on that? All right, so as I said, that's the last Chapter 7's topic that will be on this homework assignment for this week, but there is one more thing we need to cover in Chapter 7, which won't be until next week's homework assignment, but we're going to get to it today. And the last thing that your book covers with relation to enthalpy changes and heat and all that stuff is sort of the technological or industrial importance of enthalpy, and really the area where that's going to be critically important is in fuels and other forms of energy usage and energy generation. So that we're going to go through that. This is going to be not particularly systematic or conceptual. It's mainly just going to be a little bit of background information on this important, societal topic that is related to the topics we've covered in Chapter 7. So first, let's give a sort of precise definition of a fuel. So we kind of have, an intuitive sense of what a fuel is. It's something that we burn to get energy. And that's really what the chemistry definition actually is. But it's a substance that has a lot of stored energy. So remember we talked about, energy being stored as either potential or kinetic energy. And so the potential energy of the chemical bonds in a fuel, there's a lot of that energy. And so there's a lot of energy stored in the bonds of that fuel. And then you can release that energy usually by burning the fuel. If you've heard of fuel cells, that's another way of releasing stored energy in fuels, which uses more like electrochemical approaches, which we don't cover in Chem 1. You'll see it in Chem 2. So there's other ways of releasing the energy, but most common way and the most widespread way is just burning them. And so when you burn that, as you know, burning anything is an exothermic reaction. You release that energy in the form of heat, and then you can use that to do work on your car or work to generate electricity or whatever you need it to do. So that's what a fuel is. It's a substance that stores that. And the vast majority of the fuels we use on planet Earth are called fossil fuels. And so these are going to be formed from the decomposition of living organisms over millions of years. So as we'll see in a little bit, most fuels have a lot of carbon in them. We know that living things are also made up of a lot of carbon. And so when they die and decompose over, many millions of years, often with high pressures and or high temperatures involved, they're going to produce these substances that we can then dig out of the ground and use as fuels. Okay? And so again, most fuels that we use today are fossil fuels. So that would be, when you go to the gas station, when you fly an airplane, or a lot of the electricity they're moving, with electricity generation it's starting to become more varied, but still a lot of electricity is also generated with fossil fuels, natural gas, coal, and things like that. So those are what fossil fuels are, and that's, again, the primary type of fuel that we use here on planet Earth. So let's talk about the two major types of fossil fuels that we have. So one of them is called petroleum, and being in Houston, you're likely familiar at least a little bit with what petroleum is and the industry that is built around it. And so petroleum is mostly made up of hydrocarbon substances. And it's a complex mixture, so there's, petroleum is not a single compound, a single substance that has a specified composition. It's made up of a lot of different hydrocarbons as well as many other components as well, but hydrocarbons are the major fraction, which are going to be compounds that have just carbon and hydrogen in them. So some number of carbon atoms, some number of hydrogen atoms. And again, the stuff that's in petroleum is used to make a lot of liquid fuels like gasoline and things like that. So those hydrocarbons are the primary components of those types of fuels. So CXHAHY, so it's just a hydrocarbon is a compound that has carbon and hydrogen in it, in some ratio, in different different numbers of carbon atoms, different ratios of carbon to hydrogen. There's a lot of possibilities there, and it's a huge mixture of things when you just dig it out of the ground. And where you get it from is going to some extent, determine the composition anyway. So petroleum that you dig out over on this side of the world may not be exactly the same as the petroleum you get from another part of the world, and so on, but it's always going to be primarily composed of hydrocarbons, and those are very useful substances to then extract. So when you dig petroleum out of the ground, it's going to be a liquid. So when you first get it out of the ground, it's often referred to as crude oil. When it comes right out of the ground, it's kind of a messy, disgusting liquid. But then what they do is they do a bunch of processing of that liquid, a bunch of physical separations, in some cases some chemical reactions on components in that liquid, and they separate out the different useful components. And there's a whole lot of useful components in there, but the ones that are used as fuels are primarily of three types. So there's gasoline, which of course would be what you would all use in your cars. diesel, which is used in some cars but more in heavy machinery, and then jet fuel is the third sort of common type of fuel. But these aren't the only things that you get from petroleum. There's a whole lot of other substances that come out of petroleum as well. So the precursors to make a lot of plastics come from petroleum, and other lubricants and things like that come from petroleum. So there's all kinds of things that come out of petroleum besides these, but in terms of fuels, those are the three major types: gasoline, diesel, and jet fuel. The other major type of fossil fuel is coal. So coal is mostly made up of carbon, so it doesn't have a lot of hydrocarbons in it. It's mostly just carbon by itself, and it's a solid. And the key idea here is, there's variable carbon content. So again, depending on where you get the coal from, it might have higher percentages or lower percentages of carbon. Again, it's always going to be mostly carbon, but exactly what percentage depends on the type and the grade of coal. So your book lists, a few different types of coal. I don't even remember the names of them now off the top of my head. They're mineral names essentially, but and different carbon percentages. But the key concept, we don't want you to memorize the different types of coal that we have, but we want you to understand the concept that the higher the carbon percentage in the coal, that's going to mean there's more stored energy. So the energy content of coal is dependent upon the percentage of carbon that's in there. All right, so if it's, I think the highest percentage for the most common types of coal is like 92%. So that's going to have more energy than another type of coal that's, let's say, 70-some% carbon. So they vary a little bit, and the more carbon it has, the more stored energy it has. And that's, if you want to know why that is, that's because when you burn coal, you're primarily converting that carbon into carbon dioxide. We know that in a combustion reaction, carbon dioxide is typically one of the major products. And coal that has less of the carbon percentage in it, some of the carbon is already sort of oxidized already in some form by oxygen. It's not in the form of CO2, but it's in other forms of CO products. So you're not able to generate as much energy when you burn that, because you're not able to make as much CO2, which has those strong carbon-oxygen bonds that release a lot of the energy that you would have in a fuel. Okay, so the key concept though is the more carbon that coal has, the more higher percentage it has, the more stored energy would be in that coal. All right, so any questions so far on just the basics of fossil fuels? Yeah, Kyle?
What's the fuel? Like the definition of fuel again?
So the definition of a fuel is it's a substance that has a lot of stored energy, and usually that energy is released by burning it, by decomposition of living organisms. So that's why we call them fossil fuels, because they come from organisms that lived hundreds of thousands or usually millions of years ago. All right, so those are the types of fossil fuels. Now, as you might recognize if you read the news on a regular basis, there are concerns about continued use of fossil fuels. And so one of those is concerns about the effects of greenhouse gases on our atmosphere. So things that you produce from fossil fuels, which include water vapor when you burn them, or fossil fuels also have some methane mixed in. Now, methane we can use as natural gas, but when you're collecting fossil fuels, a lot of times that methane will get released into the atmosphere as well. And then, of course, when you burn fossil fuels, you also get a lot of carbon dioxide out. So these three gases, among others in the atmosphere, they trap heat, and so there's concerns then about how that's going to affect the temperature on the surface of the Earth. And I'm not a geologist or a climate scientist, so I'm not going to try to go into the details on that. That's outside of my purview, but nonetheless, these are concerns that you're likely aware of. These, this greenhouse gas effect and the effect that it would have on global climate if we continue to just burn fossil fuels and release all these gases in the atmosphere and significantly change the composition of the atmosphere from what it was. All right, and so again, that's the main concern. If we just continue increasing greenhouse gases in the atmosphere, if we continue burning fuels and releasing those, that may lead to unsustainable, unnatural warming of the Earth. So that's one of the primary motivations for getting rid of fossil fuels and moving on to other things. The other thing that you have to think about a little bit, I mean, it's not going to matter in our lifetime, but it's something to think about over the next hundreds or thousands of years as we hope to keep human civilization alive for that long. which is the long-term viability of fossil fuels, because there's sort of a sort of a time scale imbalance, right? As I said, it takes millions of years to form these fossil fuels, and we're using them at a much faster burn rate than they're going to be actually generated in the earth. And so you have to worry about, are we going to have enough fossil fuels to last for how many years, right? And they keep sort of revising the estimates for how much fossil fuels reserves we have, and it's at least on the order of hundreds of years. We don't really have to worry about it. But fossil fuels won't last forever because they take millions of years to replenish. So we're going to burn them all out eventually before they're all replenished. So you need alternative sources of fuel that don't have this issue, that you can generate much faster, and are ideally not going to also then lead to different things in the atmosphere that might cause various problems. So that's some concerns about fossil fuel that has then motivated a lot of research development into alternative forces beyond fossil fuels. So there's a couple that your book mentions, so this is not a comprehensive overview, but just to sort of finish this off and make sure you have the essential information that you need for homework assignments and tests. So if you read the book, there's a lot more details, and I encourage you to, because I think it's interesting stuff. But I'm giving you here what I think is sort of the important and essential concepts for what you need to do on assignments in this course. So one potential energy source for the future is hydrogen. Now, if you're familiar with the Hindenburg disaster, you know that there's some also valid concerns about using hydrogen. It's very explosive and very high temperature when it burns, but it has a very high energy density, at least in terms of its what's called gravimetric energy density, the energy that it stores per unit mass. All right, because when we burn 1 mole of hydrogen, you just make water. It's a very simple reaction, but it releases a lot of energy. Delta H is minus 286 kilojoules. And hydrogen is one of the lightest substances in the world, probably the lightest substance in the world, only has a molar mass of 2 grams per mole. So you're releasing a lot of energy for not a lot of mass that you need to burn. So it's a very high energy density in terms of how much energy it stores per gram. And it only makes water as a product, so there's the concerns about CO2 you don't have to worry about. And in principle, although there's not really a great economical way to do this yet, you can take the water, collect it, and then recycle it to make more hydrogen. So basically you can get this sort of ideal closed loop where you burn hydrogen to release energy, and then you put some energy back into water and make more hydrogen and kind of just cycle the whole thing around. So that would be nice if it worked. And it has a very high energy density, so it's good from that standpoint. But the problems are right now that hydrogen is expensive to produce, so it's not cost competitive with fossil fuels yet, and whether it ever will be, I guess, is the topic for the future. And the biggest issue with hydrogen, though, there are ways to use it, and there are fairly mature technologies like hydrogen fuel cells and things that we can, and there's sort of prototype devices out there that do that. Well, hydrogen is difficult to store and transport. It's a gas, first of all. Liquids are, in general, much easier to store than gases because they take up a lot less space, as we'll learn in Chapter 8. But also, hydrogen, as we said, is explosive and can, there's very, very high potential for accidents when you're using hydrogen for explosions and fires and things like that. So that's the main concern with hydrogen. How do we store it and transport it in a safe way? Because, if you want to, I think in terms of the volume, so you typically fill your your car with, like, let's say 10 or 15 gallons of gas, depending on what depending on what kind of car you have. If you were going to fill your car with hydrogen to be able to drive the same distance, I don't remember off the top of my head the difference, but it's going to be a factor of 10 or 100 times more hydrogen that you need in terms of volume, because hydrogen is a gas and intrinsically takes up a lot more space. Even if you compress it, it's you can't compress it too much, or again you run into serious safety concerns. So there's this volumetric problem that if you wanted to run a car off of hydrogen, you'd have to have a huge storage tank to hold enough hydrogen to drive your car for the usual 300 miles or so that you need to go before you want to fill up. So hydrogen has problems with storage. That's really limiting its development. Now, another common technology that's being developed is called biofuels. So these are fuels that are generated from plant matter or produced by microorganisms. And the nice thing here is that they use essentially photosynthesis. They're using sunlight as the sort of essential source of energy for this to produce these fuels, and it can be done much faster than millions of years. So it doesn't require decomposition of these organisms. It's just that these certain plants and certain animals can generate substances that can be used as fuels, and they can do that much faster than it would take for fuel to form naturally in the ground. A lot of them are similar types of molecules to what we already use, so you wouldn't have to sort of rehaul the whole infrastructure. So most biofuels that are commonly developed these days are alcohols, so methanol, ethanol. Again, if you pay close attention at the gas pump, you know that there's already about 10% ethanol in your gas. And so it's not as good as gasoline in terms of just trying to run a car off of it directly, but there is an infrastructure in place for using ethanol, so there's some value there. And then another one is called seed oil. So certain plants produce oils in their seeds that are pretty high energy density and behave in a similar way to things like petroleum sources. So that's just a little bit of background about where the world potentially is going to be going. Again, these are not mature technologies yet, and there's a lot of alternative ideas about how we should do things that I'm not even covering here, but this is kind of some things that your book goes over, and it's all related to enthalpy, because again, when we're dealing with fuels, whatever type we're using, is all about the idea of storing energy in chemical bonds and then releasing that energy when those fuels are used. And so it's all related to the topics that we've covered in Chapter 7. All right, so any questions on that last Chapter 7 material before I move on? Yes? It's H2 plus O2 going to H2O, and then this is just showing that in principle, although there's no great way to do this yet, once you form the water, you can convert it back to hydrogen. So it's just like reversing the reaction. And so what you're so sort of an ideal dream world, but again, we're not there yet, would be you use some sort of renewable energy to split the water into hydrogen and oxygen. So if you use like a solar panel or wind energy or something like that, that splits it, and then you store that energy as hydrogen, and then when you need to release that energy, you burn it to get the water back, and you just kind of keep going around this cycle without ever having to use fossil fuels, ideally. But again, we're a long way away from that being a reality. All right, so any other questions? Okay, so that takes care of Chapter 7. And so what we're going to move on to for the last two chapters of this course, we're getting dangerously close to the end, or I guess exhilaratingly close to the end, depending on your view of this course, is we're going to cover in chapters 8 and 9, we're going to cover the different states of matter. So solid, liquid, gas, which you already have some familiarity with. And we're going to talk about the different molecular interactions and different properties that result from these different states of matter. So chapter 8 is about gases. That's what we're going to start with. But let's first do a quick overview of all three of them so we can kind of see the differences. So a solid is something that has a fixed volume and shape. So this little graphic here is sort of a badly drawn cartoon of ice, which would be frozen water. So it has a fixed volume and shape, and that's what we would refer to as solids. And most of the, all the materials that are used to build this classroom, of course, are solid. And then we'll talk about solids in Chapter 9, and same with liquids. That's going to be something we'll talk at least a little bit about in Chapter 9. There's not as much things we can talk about with liquids, but we'll talk about some things with them. And the difference with liquids is they still have a fixed volume, but the volume conforms to the shape of the container. So they're fluid, they can flow. And liquid has an upper surface, so it doesn't just expand in all directions. It has an upper surface that sort of bounds it to a specific volume, but it can spread out in all the other directions and fill whatever available container shape it's in. So it's able to freely flow, unlike a solid, which is more rigid. Has an upper surface, yeah. All right, and then the one we're going to talk about in this chapter in a lot of detail are gases. So a gas completely fills whatever container it's in, so it doesn't have a fixed volume. If you release a gas into any contained area, the gas is going to fill that entire container. It just like a liquid is freely flowing, but it does not have an upper surface like a liquid, so it can flow in all directions. And another key aspect of gases is they have low density. So we just talked about that with hydrogen. So one of the difficulties with hydrogen, it has a really low density, which means that its mass to volume ratio is small, at hundreds or thousands of times smaller than a typical liquid or a gas. So liquids and gases are much more dense. Liquids and solids are much more dense than gases. All right, but that's the key thing. And what we're going to sort of talk about throughout this chapter and throughout the next two is what sort of determines the macroscopic state of the matter, the solid, liquid, or gas form, is how the molecules or atoms are arranged and how they're moving around. So in a solid, the atoms or molecules that make up the solid are very much fixed in place. They can, vibrate around a little bit, but they're not freely moving around. They're kind of rigidified, they're held together by certain forces in a certain orientation. In liquids, the molecules are moving, but they're all kind of still in contact with each other. So they're kind of like rolling all over each other. So they're able to move, but they're still very much in contact. But then in a gas, as this sort of picture shows, this would be water vapor, all the molecules are really far apart and they're zinging around in all directions and they don't really have contact with each other. So that's kind of the difference in terms of the molecular level, which are concepts that we're going to develop in more detail as we go through all of this. So the first thing we need to talk about when we're understanding the properties of gases is a concept called pressure. Now we introduced pressure just a little bit in chapter 7 when we talked about expansion work, the expansion of a gas against a constant pressure and how much work that involves. But we're going to cover it in more detail here, and that'll help make that last stuff a little bit more sensible, I think. So pressure is force divided by area. So because gas molecules are constantly moving and because they fill the container that they're in, whatever container then they're going to be constantly pushing against the walls of that container. So that's the force that they exert, and that force normalized to the area of the surface that they're pushing against would be what's called the pressure. Okay, so we're going to talk a little bit about how you would measure pressure in this course. And there's sort of two ways to do it. So if you want to measure the pressure of the atmosphere, the gas that's sort of around you, you would use what's called a barometer. So you've probably heard of barometric pressure if you follow weather reports. And the way a barometer works is, again, it's a device that's used to measure atmospheric pressure. So the way that it works is that you have, the simplest ones anyway, they have a dish of a liquid. Now the liquid that's often used in these is mercury because it's exceptionally dense. If you were to try, you can make barometers out of water, but they'd have to be I think 3 stories tall or something to be useful. So it's just not practical to use something that has pretty low density like water, otherwise you need a huge column for this to work. But for mercury, because it's really dense, the column height is roughly about 1 meter tall. So if it was on my table, it'd be about this high. And the way it works is that you have basically a balancing of the two forces. So there's mercury here in the bottom of this little dish, and then there's an inverted closed tube that the mercury can flow up into. And so the pressure of the gas pushes down on this, and then the weight of the mercury sort of opposes that, and when those two things are equal, the mercury will stop rising in the tube. So if the pressure increases and the gas is going to push down harder, the mercury will rise up the tube a little bit. If the pressure decreases, then the mercury will fall down a little bit. So basically the height of that mercury column is a direct measure of pressure. And I'm not going to sort of derive the mathematical relationships for why that is, but basically you just need to measure the height of this mercury column, and that will give you directly the pressure. So there is one unit of pressure that's going to be directly reporting the height of a barometer column. So it's going to be called millimeters of mercury. So if you're at atmospheric pressure at sea level or close to sea level, that pressure is going to be close to 760 millimeters of mercury. So that means the mercury column would be 760 millimeters tall at atmospheric pressure. And the reason we don't use water is because in terms of water, that would be about 34 feet tall. So you'd have, again, about a 3-story barometer to be able to do it with water. So we use mercury for that purpose because you can use a more reasonable size. And it's about 760 millimeters would be the height of a mercury column that's reading atmospheric pressure. Now the other way to measure pressure is called a manometer. And this would be to measure the pressure of a sample of gas. So if you're doing experiments on gases, then this is the sort of low-tech way of measuring the pressure of that. So there's two types of these as well. So one of them is a closed-end manometer. So in a closed end manometer, they both kind of look the same. The only difference is whether this end here is completely closed off or open to the atmosphere. So in a closed manometer, what you have is you have your little bulb here that has your gas in it, and then you have sort of a U-shaped column of mercury. And so what happens then is when you release the gas, it's going to push down on that column there. So initially they're going to be at equal height, and then it's going to push down, and this is going to raise up on this side, and the two, as they're showing here, will be unequal in height. So basically when you have gas pressure in there, it's going to push down on one side of that U-shaped tube of mercury, it's going to push it up, and the two sides are no longer going to be the same height anymore. So in a closed end manometer, you're measuring pressure relative to vacuum. So on the other side of the column of mercury up here, where there's this closed tube, there's no pressure at all. So when there's no pressure, we say that's called a vacuum. And in this case, the difference in height between the two sides of your column, that there to there, is going to be directly equal to the pressure of the gas. You just have to measure the difference in height, and that'll give you the pressure of the gas in millimeters of mercury. Now the other type is called an open-end manometer. So in an open-end manometer, let me put a little dash line between this to keep them straight from each other. That's shown here on the right. Again, it looks very similar, but now the end of this tube is open to the air. It's no longer closed off. And so in this type of manometer, the pressure is going to be measured relative to the atmospheric pressure. So the pressure of the gas is going to be equal to the atmospheric pressure plus or minus the difference in height between the two sides. And this is showing the two possible situations. So here, I think you can kind of see it. These drawings are not showing up great on the slide, but on the screen. But in this left-hand one here, what you'll see is that the tube is higher on the side of the gas. And so what that means is that the gas pressure is lower than atmospheric. So basically you have the gas pushing on one side, the atmosphere pushing on the other side, and whichever of those is stronger, that's going to push the column down further. So here, we have gas pressure higher on the side that's connected to the gas, lower on the side that's connected to atmosphere, so that means the gas pressure is lower than atmospheric. Here, the opposite. Here, the tube of mercury is lower on the side that's being acted on by the gas, and that means the gas pressure is larger than atmospheric. There's an imbalance of forces in that direction. So it's going to be, the pressure of the gas is going to be the atmospheric pressure plus or minus delta H. Plus delta H if the gas pressure is higher, like it is over here, minus delta H if the gas pressure is lower, like it is here. So those are two types of manometers. And as far as I know, there's still going to be, maybe like one homework question on those, but it's not a big deal for this course. But that's just some background on how pressure is measured. And when we're using manometers and barometers, that's going to be reported directly in millimeters of mercury, the height of the liquid column that we're using. Okay? So that's sort of the basics. Now we have to talk a little bit about units of pressure, because we use millimeters of mercury. It's still useful in some contexts, but it's not the only unit. So let's talk about different units of pressure. So the SI unit, the one that would be sort of considered standard, although it's not very commonly used, is called the Pascal. It's abbreviated as PA. It's named after scientist Pascal. And so 1 Pascal is just, again, force divided by area is pressure. So the SI unit for force is Newton. If you've taken physics, you've seen that all the time. And the SI unit for area is square meters. So Pascal is 1 Newton per meter squared. Where again, N is Newton, a force unit, and that's in SI units, kilograms, meters per second squared. So all of these are derived from standard SI units. Kilograms for mass, meters for length, seconds for time. That combined unit is called a Newton, which is the SI unit for force, and then divided by area gives you the SI unit for pressure, which is called Pascal. Pascals are not used particularly often, though, as we'll see. The most common one that we'll see in this course is atmospheres. And this is going to be the average barometric pressure, or atmospheric pressure. And we measure atmospheric pressure with a barometer. So basically, atmospheres is a unit of pressure that was scaled to life on planet Earth. We just measure the pressure of the atmosphere at sea level, kind of the average value that you get. It does fluctuate. Is referred to as 1 atmosphere. So the relationship to pascals is that 1 atmosphere, so pascals is actually a very small unit of pressure. So 1 atmosphere is 101.3 kilopascals, so 101.3 thousand pascals, or 1.013 times 10 to the 5th pascals. And then that's equal to 1.013 bar. So 1 bar is 1.01 times 10 to the 5th pascal. So bar is an SI unit for pressure, it's derived from SI unit, and is very similar to atmospheres. So to all practical senses, they're about the same, but 1 bar is 1.013 times 10 to the 5th pascals.
Wait, when you say 1 K equals 101.3 K, is that?
Kilopascals. So that's 101.3 thousand pascals. So kilo is the prefix that means 1,000. All right, so that's going to be the relationships between those units. And then another one that we'll see is called torr, which is short for Torricelli, named after an Italian scientist. And 1 torr is equal to 1 millimeter of mercury. So it's just an alternative way of saying millimeter of mercury. So those 2 units are used interchangeably. And then the most important pressure relationship, I'm giving you basically 4 different units of pressure, which is kind of annoying, I realize. But the most important relationship, the 2 that are going to come up the most in this course, are going to be the relationship between torr and atmosphere. So we said in the previous one that when you measure atmospheric pressure at sea level, it tends to be about 760 millimeters of mercury. So 760 millimeters of mercury, or 760 torr, is equal to 1 atmosphere. So torr and a millimeter of mercury are the same, and 760 of those equals 1 atmosphere. And those are the pressure units that are used most commonly in a chemistry context. Even though pascals is the SI unit, and even though bar is sort of derived from that, we're going to still primarily use atmosphere and torr in chemistry. All right, so any questions on units? So those are some new unit conversions you'll have to do from time to time, so make sure we get familiar with them. So then so let's just do an example of that, just to use those conversion factors. We've been using conversion factors all year, so this shouldn't be too much of a hassle. So if we have a compressed gas cylinder, so yet another unit for pressure that I didn't introduce yet is PSI. So you might be familiar with PSI because when you fill your tires and you look at the pressure you're supposed to fill your tire to, it's usually reported in PSI, which is pounds per square inch. So that's an English unit, one of those annoying units that we like to use here in the United States and other parts of the Western world, even though they're not very friendly. But anyway, compressed gas cylinders, if you buy a cylinder of helium to blow up balloons, well, please don't do that because helium is very valuable and we don't want people wasting it in balloons. But if you did, you would buy a cylinder and they're usually at about 2,000 PSI. So we want to know what is the pressure in millimeters of mercury. So this conversion you don't need to memorize. PSI, again, is an English unit, so it's not intuitively related to atmospheres, but that's given to you here. And then, of course, this relationship is one that we have to use a lot. All right, so it's just going to be a series of conversions. The pressure in millimeters of mercury, if we have 2,000 PSI, first we're going to convert PSI to atmospheres because we have that conversion there. So 1 atmosphere is 14.7 PSI. And then once we have atmospheres, we can easily go to torr because it's 760 torr per atmosphere. That conversion you'll need to know, as I said. And then the last trivial step would be, or we could have just done this, combine these 2, is that torr and millimeter of mercury are the same, so it's just a 1-to-1 conversion to go into millimeters of mercury. So that comes out to 1.03 times 10 to the 5th millimeters of mercury, which is around 100 meters of mercury, which I didn't ask you for, but just to give you an idea of how big that number is. All right, so that's that would require, if you're going to use one of those low-tech barometers or manometers that I described on the first slide of this chapter, if you're going to use one of those to measured the pressure at this level, you're going to need one that's 100 meters tall, which is impractical. I mean, that's going to be 300 feet tall. It's like a 30-story building or something. So again, those barometers and manometers, they're good for measuring relatively low pressures that are close to atmospheric pressure. But if you're trying to measure really high pressures like this, there's more sophisticated, in these days, electronic devices for doing that. But that would be the pressure that you get inside of a cylinder, which is, again, in terms of millimeters of mercury, quite a large number. All right, so any questions on pressure units? All right, so the next thing we're going to move into are what are called the gas laws. So these are relationships between the properties of a gas. And there's going to be basically 3 gas quantities that we're going to relate to each other: pressure, volume, number of moles, and temperature. We're going to talk about all 4 of those and how they relate to each other. And all of the gas laws are basically relationships that involve the volume of the gas. So how does the volume of a gas change when the pressure, the number of moles, or the temperature of that gas changes? So we're going to derive individual gas laws that deal with the response of the volume to those other things. How are they related to each other? So the first one we're going to talk about is Boyle's law. So this gas law and all of them require basically a constant temperature. So we're keeping the gas temperature constant in this case for Boyle's law. And we're using a closed container, which means that gas cannot escape from the container. So, an enclosed system. So let's look at the relationship then between volume and pressure. So Boyle's law deals with the relationship between volume and pressure. And so let's watch a video to see what happens there. Okay, so this is a Boyle's law demonstration. So what they're going to do here is they're going to put a balloon inside of a chamber, and they're going to use a vacuum to basically pull all the gas. So they're reducing the pressure inside of this container by pulling all the air out with a vacuum pump, and you can see that the balloon is getting bigger and bigger. So as the pressure around that balloon decreases, the volume of the gas inside the balloon gets bigger and bigger and bigger. And you can see it's going to start filling up the whole container as the pressure continually decreases. So that tells us that there's an inverse relationship. Now they're letting the gas back into there, so they're venting the container, and you can see as the pressure increases, the volume gets smaller again. So now he's going to do the same thing with a marshmallow peep, which has a lot of gas trapped in it. We're close to Easter time, so this is appropriate. And we're going to see what happens when you lower the pressure around a marshmallow peep, and you can see that it also expands its volume because there's gas trapped inside of there that's expanding as the pressure is lowered. And then when you repressurize it, well, the peep doesn't look so good anymore. So now he's going to do it with shaving cream, which also has gases trapped in it. So you lower the pressure inside of the container, and the gas that's trapped inside of the shaving cream expands, and you can see that the volume gets bigger. All right. So the balloon one was probably the most useful. The rest of these are just kind of visually appealing. But you can see the volume is increasing as the pressure decreases when they're pulling a vacuum on that, removing all the gas from there. All right, so let's close that so we don't autoplay another one. And then, so what we found in that demonstration then was that volume and pressure are inversely related. When the pressure was decreased, the volume got bigger, and then when we added pressure back in, the volume got smaller again. So we would write that mathematically as volume is proportional to 1 over the pressure. All right? So again, mathematically that says V is inversely proportional to P. And this is what we call Boyle's law. So Boyle is known as one of the first real chemists, and a lot of the experiments he did were studying the properties of gases, and this is one of them that he came up with. Now, if we want to write this as an equality, we could write this as V is equal to some constant divided by P. Remember, if we have a proportionality sign, we just add a constant to one side, we can change it to an equal sign. But this is not a particularly useful equation because this K here, this constant, is not well defined. It depends on how much gas we have, it depends on the temperature, it depends on other things. But what we can do is we can rearrange this, and pressure times volume is equal to a constant K, so we're just going to cross multiply. So if the product of pressure and volume is always constant, because again K here is just some constant, then what that means is that for a given sample of gas, the product of the pressure and the volume will always be constant. So if we change the pressure and the volume P1V1, the initial pressure and volume, will be equal to the product of the final pressure and volume, P2V2. So this is a mathematical statement of Boyle's law. When you have an inverse relationship between two parameters, pressure and volume, like we do here, then you can set up this equation to relate the initial and final state of that gas as the pressure and volume are changing. So P1V1 equals P2V2 looks a lot like M1V1 equals M2V2, but this time it's in terms of pressure and volume for our gas. Okay, so that's the equation that deals with Boyle's law. Now as we go through this, we're going to come up today with 3 separate equations for 3 separate gas laws, but then as we'll talk about next time, there's a way to combine all 3 of them into one equation, which is really the only equation you absolutely have to know to be able to drive all the rest. But we're going to start with 3 individual equations, and this is the first one. So let's just do a quick example of how it's used. So let's say we inflate a balloon at sea level, where the pressure would be 1 atmosphere. And then if the balloon rises to an altitude of 6.5 kilometers, so it's a helium balloon and it just goes off into the air, and then the air pressure at that height is much lower, 0.4 atmospheres, what will the final volume be? Ignore the balloon's elasticity and also assume that the balloon won't pop, obviously, as it gets expanded too much. All right, so what we can see in this problem here is that we're assuming a constant temperature, and it's a closed container, it's a balloon, so as long as the balloon's not leaking, there's not going to be gas coming in or coming out. So we can use Boyle's law here, because all that should be changing is pressure and volume. We're starting with some volume at the pressure that corresponds to sea level, and we're changing the pressure. We want to know what's the volume going to be at that new pressure. So we'll use P1V1 equals P2V2. And for this equation here, it doesn't matter what units we use as long as the 2 volume units are the same and as long as the 2 pressure units are the same. So you can use whatever you want because they'll divide out when you rearrange the equation. So we're looking here for the final volume when we change the pressure. So it's going to be P1V1 over P2. And then we have to plug in the numbers. And like I said, the units don't matter because as long as the 2 pressure units are the same, they'll divide out. And then the answer will be in whatever units we use for this V1 here. So the initial pressure was sea level, so that's 1 atmosphere. I didn't explicitly say that, but at sea level, the pressure is 1 atmosphere. And the initial volume of the balloon was 0.5 liters. And then as it rises up into the atmosphere and the pressure decreases to 0.4 atmospheres, we'll divide by that. That's our P2. So atmospheres cancel out, and that gives us a new volume in liters, which is 1.25 liters. All right, so the volume of the balloon will slightly more than double as it goes up to that higher altitude with a lower pressure. And again, there's an inverse relationship between pressure and volume, so as the pressure decreases, the volume of the balloon gets bigger. This is how it works out mathematically. All right, any questions on that? Okay, so the next one we're going to talk about is what's called Charles's law. So this is a relationship between volume and temperature. So here we're going to keep the pressure constant. So isobaric means constant pressure, and we're going to keep the number of moles constant. But we're going to look at what happens to the volume of the gas as the temperature is changed. As the temperature gets lower or higher, what happens to volume? So we have another video for that. So what they're going to do in this experiment, it's going to start pretty quickly, is they're going to take a balloon that's filled with gas that they just blew up probably normally, and then they're going to put it into liquid nitrogen to lower the temperature of that gas to a very low level. So it's initially at room temperature, which is like 295 Kelvin around there, and then they're going to put it into gas or into liquid nitrogen where the pressure is like the temperature is 77 Kelvin. So it's going to drop the pressure drop the temperature a lot as they do that. Okay, so here's what they're going to do. So they're going to cool the balloon down in liquid nitrogen. I would not recommend doing this with your bare hands, but they did, so I hope they didn't hurt themselves. You can see a little bit of marks on his hand. What if those are liquid nitrogen burns? Anyway, you can see though the volume of the balloon is shrinking. So as the temperature goes down, now he's finally using a little bit of safety equipment, the volume of the balloon shrunk considerably. And now he's going to let it warm back up, and just using the air around it to warm up, and as it warms back up, the volume gets bigger. So basically when the temperature is higher, the volume is larger. When the temperature is lower, the volume is smaller. Okay, so that was the relationship between volume and temperature, and those two then are going to be directly related to each other. All right, so when the volume got bigger, the temperature also got higher and vice versa. So volume is going to be proportional to temperature. Directly proportional is how we would say it. So that means we can write this as an equal sign by just putting a constant on one side. It's not the same constant we had in the last one, so I'll call it K prime. But again, it's not a very useful constant because it depends on the pressure and the number of moles of gas that we have. So it's not going to be a fixed constant for all situations. But we can rearrange this equation by just dividing both sides by temperature. And then we can say that V1 over T1 equals V2 over T2. So this would be a mathematical form of Charles's law, where volume and temperature are directly correlated to each other. So in this case, the fraction V1 over T1 will equal the fraction over V2 or T2. As we change the temperature and the volume responds, those relationships have to stay constant. Volume divided by temperature has to be a constant. Okay.
V equals K equals that.
That's a little prime next to K. Just to tell you that it's not the same K that we had in the last example. Again, we're not actually going to use this equation because K is not a well-defined constant. It's dependent on how much gas you have and all these other things, so we're not going to use it. But whenever you have a situation like this, you can just rearrange the two, and you'll say that volume divided by temperature is equal to a constant. So for a given sample of gas where all you're changing is volume and temperature, then you can set up this relationship here. The ratio of the two has to stay constant, which means the ratio of the two before and after that change will be equal to each other. Now in this case though, we have to be very careful with units. In this case it does matter for the temperature in particular. The temperature here must be in absolute temperature, Kelvin. All right, so we have to start getting used to this. Whenever we're doing calculations involving gases where the calculations involve the temperature, it has to be in Kelvin. It cannot be in degrees Celsius. All right, and again, we have to remind ourselves that the temperature in Kelvin is going to be the temperature in degrees Celsius plus 273, technically 0.15, although if you leave out the 0.15, it's not going to cause your answer to be off by enough to cause an issue. Come on, erase. All right, so temperature in Kelvin is Celsius plus 273.15, and that's the unit we have to use for any of these gas law problems, because here it's an absolute temperature. In Chapter 7, we did a lot of problems with delta T, which was a change in temperature, and in that case, Celsius or Kelvin was fine because the difference between two temperatures in those units is the same. But here we're talking about an absolute temperature scale, where we need to use Kelvin because that's the one that starts at 0, that's the lowest absolute temperature, and then goes up from there. So you have to use Kelvin for any problems involving gases where it's the absolute temperature that's in the equation, not a delta T. All right, so that's Charles's law mathematically, so here's an example of it. So let's say we have a sample of gas has a volume of 79.5 milliliters at 45 Celsius. What volume would it occupy at 0 degrees Celsius if the pressure were held constant? So this again is an example of Charles's law because it's a sample of gas. We're not telling you that we're adding or removing gas, so it's the same amount of gas, and we're telling you that the pressure is constant. So the only thing that's going to be changing then is volume and temperature. So we're going to use that equation we just introduced for Charles's law. V1 over T1 equals V2 over T2. And so what we're looking for here is the new volume when we lower the temperature. So this is our initial volume V1 and our initial temperature T1, and this is our final temperature T2. So what we're looking for here is V2, which is going to be, if we just cross multiply both sides, V1 times T2 divided by T1. Now this right away shows us what the problem is if we use Celsius units. So if we drop the temperature to 0 degrees Celsius, if we use those units, that would suggest that the volume is also going to go to 0 because T2 would be 0. And we know that you can go to, think about it, we've had some days this year that were 0 degrees Celsius, that's basically 32 Fahrenheit, and the volume of gases in the world didn't collapse to 0 on that day, so we were all fine, maybe a little bit cold, but we didn't have our whole world collapse to zero volume. So you can't use Celsius temperature, you have to go to Kelvin, which is the absolute scale. So that we have to convert both of our temperatures into Kelvin before we can use them in this equation. So the initial temperature in Kelvin is 45 degrees Celsius. And again, technically it's plus 273.15, but if you just do it as 273, that'll be close enough. That 0.15 is not going to make a difference in your final answer to a significant extent. So the first temperature is 318 Kelvin. We have to do that plus 273. And then the second temperature is easier to determine because it's just 0 degrees Celsius, add 273, so that's going to be 273 Kelvin. All right. So then when we plug those numbers in, again, it doesn't matter what volume we use as long as we just keep track of what they are. So our initial volume was 79.5 milliliters. T2 on the top is 273. And then T1 on the bottom is 318 in the correct units of Kelvin. And that comes out to 68.2 milliliters. All right, and the answer makes sense because we're dropping the temperature. So based on the video we just watched, if we drop the temperature, the volume should get smaller. But it actually doesn't get smaller by a huge amount. 45 degrees Celsius to 0, that sounds like a big difference, right? I mean, 45 degrees Celsius would be pretty much the hottest day you've ever experienced in your life. That's probably, what, about 108, 110 degrees Fahrenheit. So, we don't have those days too often, but we've probably all experienced it. And then, 0 degrees Celsius would be a typical pretty cold day in the winter. So that sounds like a big difference in temperature on a human scale, but in absolute temperature is actually not that huge, and so the effect on the volume is not as dramatic as you might have originally thought when we go to the correct scale, which is absolute temperature. But nonetheless, there is a significant decrease in volume because there is a significant decrease in temperature. Okay, any questions on that one? Okay, the last gas law we're going to cover today, and as I said, next time we're going to put them all together in a more useful way, is called Avogadro's law. So this one I don't have a video for, but it's also, I think, the easiest one to think about conceptually. So in this law, we're keeping the temperature and the pressure constant, and we're relating the volume of the gas to the number of moles of the gas that we have. We actually introduced this in chapter 1. You probably don't even remember it. It was done at a very sort of basic cursory level, but Avogadro's law is actually what he's famous for, not his number, which was just named after him. But here what we're going to do is we're going to relate volume to number of moles. We're going to use the abbreviation N for number of moles. Now this one I don't think we have to think too hard about. So if you have a balloon and you blow it up a little bit, and then you just blow more gas into the balloon, is the balloon going to get smaller or bigger? I mean, we've all experienced this before, right? It's going to get bigger. So as you add more moles of gas to something, the volume will get bigger as long as the pressure around it is constant. So that one I think makes pretty intuitive sense. The more gas you have, the bigger the volume it occupies at a given pressure. So that relationship is quite simple. Volume and number of moles are proportional to each other. So we write it like that. And again, if we want to, we can write this with a ill-defined constant on one side. Volume is equal to some constant, which I'll call K double prime. Again, to distinguish that it's not the same constant in all three cases. It's not a uniform, universal constant, but it's dependent on the situation. But this gives it an equal sign, and then what we can do is rearrange. So volume divided by number of moles is equal to some constant. And so because that ratio is constant, we can write it again in the same pattern we've been doing as V1 over N1 equals V2 over V2. So two quantities that are directly related will have this relationship for the sort of initial and final states that they're in. All right, and again, that one is very straightforward to think about conceptually, because if you add more gas, you would expect the volume to get bigger. There shouldn't be any big surprises there. So that's Avogadro's law. And so let's just do a problem with Avogadro's law to wrap up today. And next time, as I said, we'll combine all of these into one more useful gas law. So let's say at a certain temperature and pressure, we have 28.0 grams of nitrogen, and it occupies 20.8 liters. How much volume does 40 grams of oxygen occupy at the same temperature and pressure? Now, one point that I'm trying to make here is I'm comparing two different gases here, but for Avogadro's law and for the gas laws in general, they apply to all gases equally. It doesn't matter what gas we have. So whether we're talking about oxygen, nitrogen, or any other gas, they're going to still follow that same relationship. V1 over N1 equals V2 over N2. And those relationships do not depend on what gas you have. They depend on the temperature and the pressure of the gas, but they don't depend on what the gas is. So when we write this relationship, V1 over N1 equals V2 over N2, it doesn't matter if we're comparing the same gas or two different gases, this mathematical relationship will still hold true. But what's key is that we need to make sure we're using the right quantities, which have to be in terms of number of moles, not any other units for the quantity of gas. So we can rearrange this. We're looking for the volume of the second sample of gas. So our initial volume, this is V1, and then we're trying to find V2 here. So V2 is going to be, if we rearrange this equation, V1 times N2 over N1. And then we just have to plug in the numbers that we have. So V1 is given to us, that's the initial volume of the nitrogen sample. We want to figure out what's the volume of oxygen, which has a different amount. So for both of these, we're going to need the number of moles. So the initial volume of gas, 20.8 liters, that's for 28 grams of N2. So we have to figure out how many moles that is. So N1 is the moles of N2, and that's going to be 28.0 grams of nitrogen. Now we're telling you here that the molar mass is 28 grams per mole. So we can't forget about everything we learned in chapter 5. These mass to mole conversions still will come up occasionally. Not so much in gas laws, but they still come up occasionally. So initially we have 1 mole of gas, N2. Then we want to figure out how much volume under the same conditions would 40 grams of O2 occupy. So our second number of moles that we're using in this equation is the moles of O2. And so we're going to convert that to moles using its molar mass of 32. So it comes out to 1.25 moles of O2. All right, so that's going to be the two numbers of moles that we use. This is N1, this is N2, so now we can just plug everything in. So the original volume for the nitrogen gas was 20.8 liters. N2 is moles of oxygen, which is 1.25. There's more moles of oxygen than nitrogen, so the volume should be bigger for the oxygen sample. So that number goes on top, and then what we get in this case is 26.0 liters. Okay? So even though in these problems you're normally just comparing the same sample of gas, you know, what happens when I change the temperature, pressure, number of moles, whatever. Here we're comparing two different samples of gas, but it still works. And this drives home the key point, which we're going to make even more explicitly next time, which is that when you have these gas laws, the 3 individual laws we did today, or the combined one that we're going to do next time, it applies to any type of gas. It doesn't matter what the identity of the gas. None of these equations matter for what the identity of the gas is. All that matters is the pressure, volume, number of moles, and temperature. Those 4 things will define any sample of gas that you have. All right, so we'll get to that next week. None of this stuff that we just did will be on the homework, but we'll get through the rest of chapter 8 next week. And if you have any questions about today's material, please come and find me.